Hello, welcome to our presentation. The title of the paper is A Data Stream Prediction Strategy for Elastic Stream Computing Systems. The paper is jointly authored by Hanchu, Zhang, Dawei, myself, Atul, Sajjanhar, and Rajkumar, Buyya. This is the contents of the paper. We will start with the introduction. In a distributed stream processing system, the transmission rate of data stream usually has high volatility. In this case, if the stream processing system can adjust resources according to the data demand, when the data stream fluctuates, the resource utilization of the system will be improved. The ideal elastic resource scheduling should accommodate the data stream traffic increase and adjust the system to increase the resource allocation in real time. And when the data stream traffic drops, the system should reclaim part of the resources in a timely manner. At the same time, if the system's resources are adjusted, when the changed data stream arrives in the system, it will greatly increase the system's response time. Therefore, if resources are adjusted in advance before the data stream rate changes, a lot of system response time utilized for resource adjustments upon data arrival can be salvaged, thereby reducing the latency of the system and improving the performance of the system. Based on the above background, we propose a data stream prediction strategy called DP Stream for elastic stream computing system. We mitigate the problem by making the following contributions. First is we develop a BP neural network model based on genetic simulated annealing algorithm to predict the change in trend of the data stream rate in the next time window of the cluster. And second is we propose a resource scheduling strategy from a systematic perspective according to the latency estimation model. Resources are adjusted for the critical operations of the critical path in the DAG to obtain a lower system latency and higher resource utilization. In stream processing systems, due to the volatility of data streams, insufficient system resources will cause system performance degradation. How to allocate resources effectively and reasonably is the main challenge faced by streaming computing platforms. At present, some researchers use predictive methods to optimize the allocation of system resources to improve system performance. The comparison between our work and other closely related works is given in this table. The proposed approach is effective for the 4 parameters shown in the table. This is the problem statement, which is explained in section 3.1. Data stream processing systems model the logic of the real-time application as a DAG, represented by this equation, which consists of VG, which is a set of n vertices, and each vertex represents a spout or bolt component. And also it contains EG, which is a finite set of directed edges. The weight associated with a vertex or an edge respectively represents its computation cost or communication cost. For each DAG, first use the graph-based depth-first traversal algorithm to find the largest path from 2. This maximum path is called the critical path of the topological graph. All nodes on the critical path are called critical operations. In the prediction model, in the BP neural network, we have shown the representations for the output result of the hidden layer, the output of the output layer, and the error between the target output and the actual output. Genetic algorithm is a kind of global search algorithm which has strong global search ability, but it is prone to premature convergence, which leads to the problem of local optimal solution. In the process of searching for the optimal solution, the simulated annealing algorithm uses a certain probability to jump out of the local optimal solution to avoid the shortcomings of falling into the local optimal solution. In the forecasting process, the genetic simulated annealing algorithm is used to replace the backpropagation process of the BP neural network and makes the initial point of the iteration continue to iterate from an initial solution and correct the weights and error thresholds of the BP network to gradually find the optimal solution. First, we get the population from the initial solution of the BP neural network according to the genetic algorithm, and then perform crossover and mutation operations on the initial population to obtain the new individuals. At this time, the energy value of the system is obtained according to the simulated annealing algorithm. Then the energy difference can be expressed as shown here. And the metropolis's probability acceptance criteria is used to determine whether to accept or reject the new state. In a data stream processing system for the data tuples, the flag of processing completion is that it and all the intermediate tuples it produces are processed by its corresponding compute nodes. So TI is used to represent the time required for the node to process the tuple. The tuple processing time is related to the processing rate of the task. Therefore, the faster the processing rate, the shorter the processing time. Hence, it is inversely proportional to the average processing rate. The time required to transmit tuples from node Vi to Vj is related to the network bandwidth. And if the instances of the two nodes are on the same worker node, the transmission time between them can be ignored. Based on the relevant model discussed in section 3 of the paper, we propose a scheduling strategy called DP Stream. DP Stream is a resource scheduling strategy based on the prediction of data stream rate. For data stream rates that fluctuate drastically, it can adjust system resources according to the stream rate before the changing data stream arrives to ensure low latency. In order to realize a timely response of stream processing applications to rate changes, it is necessary to predict the data stream rate of the next time window through the prediction model, so as to allocate appropriate resources to the application in advance. In the algorithm, the initial solution of the algorithm is obtained by the BP neural network, and the initial population of the genetic algorithm is obtained as shown in step 3. Then a fitness function is used to evaluate the fitness value of the candidates in the population. If the fitness value meets the termination condition of the algorithm, the result will be output. Otherwise, the population will be cross-mutated as shown in steps 4 to 10. At temperature, calculate the fitness value of the individuals in the population after genetic manipulation and compare it with their respective parental fitness values and decide whether to accept the individuals after genetic manipulation according to Metropolis's acceptance criteria as shown in steps 11 to 19. Gradually, the population is cooled down. After predicting the rate of data stream, DP Stream will perform resource adjustment and scheduling operations based on the data stream rate in the next time window obtained by the prediction algorithm. Firstly, execute resource adjustment of the critical operation nodes on the critical path in the DAG. Increase or decrease the number of instances of the component to match the changes in the coming data stream so as to ensure a low system latency. Then place the changed instance in the appropriate worker node according to the remaining resource capacity on the worker node to ensure the resource utilization of the system. In algorithm 2, we adjust the resources of the critical operation nodes on the critical path in the DAG. First, calculate the latency of each critical operation node, shown in step 4. When the latency of the critical operation exceeds the threshold, add and execute the instance to the node until the latency is less than the threshold, as shown in steps 5 to 7. Similarly, when the latency of the critical operation is less than the minimum value, one executor instance is reduced for the node until the latency is greater than the minimum value, shown in steps 8 to 10. Then calculate the remaining resource capacity of each worker node, as shown in steps 11 and 12. When an executor instance is placed, select the worker node that meet the resource requirements of the instance and has the smallest remaining resource capacity after placing the instance to increase resource utilization, shown in steps 13 to 16. Similarly, when releasing an executor instance, select the worker node that contains the instance and the remaining resource capacity is the largest after the instance is released, so as to generate more resources to prepare for the subsequent placement of the instance, as shown in steps 17 to 19. This is the experimental environment and parameter setup, which is explained in section 5.1 of the paper. The proposed DP stream system is developed based on STORM 2.1.0 and installed using using this environment as shown here. Experiment simulates the phenomenon of violent rate fluctuations in the online business. The data stream rate is set as a random rate, and the arrival rate range of the random rate is set to between 1,000 to 3,000 tuples per second. So the results are summarized in this table. Further, we show results for the word count application. The word count is an application used to count the frequency of words in English text. It consists of a spout and two bolt. Over here, we see the comparison between the proposed approach and the STORM default scheduler. And we see that the latency of the proposed approach is much lower than the STORM default scheduler when running word count application. Due to the constant fluctuation of the input rate of the data stream, during the 800-second observation period, the average system latency of DP stream is about 2.27 milliseconds, and the average latency of STORM default scheduler is about 4.66 milliseconds. Over here, we have another evaluation where we use top-N, which is an application for counting trending topics, including one spout and three bolt. Here we use word count and top-N as the topology for our experiments. So again, we are comparing the latency. It can be seen from the two figures that the default scheduler of STORM, the latency of DP stream is much lower. The DP stream has been adjusted in advance to deal with the rate changes, so the latency has only a small fluctuation and the overall trend is decreasing. However, the latency of the default scheduler is higher than DP stream and the overall trend is increasing. This shows that DP stream is more effective. In conclusion, the prediction model is more accurate and the proposed scheduling method reduces system latency compared with Storm's default scheduler. And we have also some future directions. Thank you for listening.